a 68 or something like that.
Let's get started. I'll hand back whatever it is I'm handing back while you're taking the in-class assignments, what I'll do. But I need you to open up the power or the blackboard so I don't have. Here's what I do know. I think there's a quiz on this. Does that sound right?
No, next Tuesday. What are you talking about?
Right.
No, not Tuesday, Monday.
So we're going to get as far as we can get on chapter 11. And really, I feel like we covered single channel exponential service. So what I'm going to focus on are the other three today. But all four of these are connected to economic analysis. And that's kind of the bottom line. You've got to take all of this and connect it to economic analysis. So we're really going to I'm going to really bring this up a lot. All right. The fluster of being late.
Only 2 minutes early and late.
Oh, you got it. Takes me 15 minutes to say. What are we doing? Here's the 6 characteristics. I would have, to prepare for this quiz, I would have the names of each of these with their variables next to them. And don't expect them to always be in this order. They could be in different order. You just have to be familiar enough to say, if it says, what's L sub Q, you got to know what I'm asking for. Or if it says, what is the probability of an arriving unit having to wait, you got to know what that variable is, or what it is to look up. Now, with economic analysis, I'm going to use words, is what I'm going to do. It's the cost per channel. Meaning, we have one employee doing this job, whatever that employee gets paid to do that job, plus benefits, that's the cost per that channel. If we have 2 employees doing the job, it's the cost per one channel. This is the number of channels. So they're multiplied times each other. I'll put the star there. You add that to, this is the cost of waiting, called the waiting cost. And that's multiplied by average number in the system. Average number of units, average number of customers, whatever you want to call it. Now I'm going to use some variables now. Number of channels is always the K. And the average number in the system is always the L. And these costs, you'll be given them in the problem somewhere. The trick to this, you can read the problem and know how many channels is being talked about. You'll be given the cost per channel. You'll be given the cost per waiting. It's the L you won't be given. And that's what you need to come up with once you decide, okay, am I reading a problem that's exponential service, or is it constant service or arbitrary? Is this multiple multiple service channels, or is it just one service channel? And don't forget, recognizing these 4, I gave you hints as make it fast for you. If the problem has a standard deviation in it, you know it's which one of the 4. Arbitrary. If it's talking about that the service being provided is the same amount of time for every single customer, exactly the same time, it's which one? Constant. And if you don't see a standard deviation and it doesn't talk about the service being the exact amount of time for each one, you know that it must be exponential. Now you've got to say, is it talking about service being provided by one service station at a time, or is there more than one at the same time? And if there's more than one, it's multiple. If there's only one, it's single. That's how you key in as to which it is. Then, we were just talking in my office, and I realized that maybe the next hardest thing to figure out is, are you reading arrivals in service is it being presented to you as time or rate? So I need to make sure you can recognize that. That wasn't even planned in today's lecture. But I can tell that this could be the next hardest part. Rate or time? Go ahead.
Is there an equal sign before L there? Is that
No.
No?
That's the number of. Average number in the system. So this is times. Let me put times. Times there, average number in the system, number of channels, cost of a channel, cost of waiting.
So what are they going to give you when you run all of this?
It's the economic analysis, your cost per unit. This will be your overall cost per unit of time, called the economic analysis. So I'm just gonna, off the top of my head, just gonna make some things up, and I need you to tell me if I just presented to you arrivals and service as a rate or time. So we gotta get past this and get to the stuff that we really need to cover. This Burger Dome has 2 cashiers. Customers arrive. I forget they have 2 cashiers. 1 cashier. Burger Dome has 1 cashier. Customers arrive in a serpentine roped off thing, and they're arriving. There's customers arriving every 5 minutes, and the cashier takes 2 minutes to take the order. Okay, this is arrivals, and this is service. In arrivals, they're arriving every 5 minutes. Is that a rate or time? Time. Service rate will always be, the words will always say, a blankety blank amount per unit of time or each unit of time. Those are the most common words of a rate. Let me say that again. It will say blankety blank amount, however many, per hour, per minute, each hour, each minute. Then it's a rate. But when it says arrivals are arriving about every 5 minutes, that doesn't tell us how many per minute or how many per hour. It's telling us how much time between arrivals. So you got to convert. Always convert everything on arrivals and service to rate. If you're not given the rate, you must convert to rate. When we get to arbitrary, though, the standard deviation is never converted to rate. That's the tricky part of all these. Let me say it again now. Every one of these, arrival has to be a rate, service has to be rate, but arbitrary standard deviations in time. So now, if this arrival's arriving every 5 minutes, and you want to convert it to a rate, and let's say you want to do per hour, how would you do that? Now, some of you know the math right off the top of your head. But for those who find this part hard, this is how I kind of visualize it. I've got a customer walking through that door every 5 minutes. So here we go. A customer's about to, 5 minutes, here's the first 5 minutes, a customer walked in. Second 5 minutes, another customer walked in. So we got 2 customers in. Third 5 minutes, 3 customers walked in. We have 15 minutes there. How many 15 minutes in an hour? 4. If there's 3 customers walking in 15 minutes, how many would be in an hour then? Since there's 4 15-minute intervals. 12. 5 minutes would turn into 12 per hour. The math would be 60 minutes divided by 5 equals 12 per hour. But if you visualize it, it kind of gets you there if you can't figure out for sure what the math is. Here's service. We're providing service on an average of 2 minutes for each customer to put their order in. And is that time or rate? Time. You got to convert this to rate. So you got to say, if I'm helping a customer every 2 minutes, so 2 minutes went by, there's 1 customer. Another 2 minutes, we're at 4 minutes, 2 customers. Another 2 minutes, that's 6 minutes, that's 3 customers. 6 minutes, 3 customers. How many 6 minutes in 60 minutes? 10. 10 times 3, 30 per hour. Now you're ready to answer the questions. And this question may be, okay, here's our arrival rate now, here's our service rate, and one of those 6 characteristics, or maybe 2 of those 6 characteristics would be asked. For example, you may be asked, since it takes 5 minutes for every arrival, between arrivals and getting the order takes about 2 minutes, you convert it to rates. What's the average time a unit spends waiting? What variable are you looking for if you calculate this? Which formula, which variable? Average time a unit spends waiting. What variable? Okay, you got to be on top of that. Say it again. No one? WQ. Now let me make sure you realize this. There's the probability of no units, probabilities of a unit having to wait. They're always P for probability. There's the average number, and they're always L's. And then there's the average time, and they're always W's. There's different W's, different L's, different P's, but the P's are probability, the L's are about average number of something, and the W's are average time of something. Okay? Thomas, I wasn't sure I got you on the video. Oh, okay, just making sure. You ready? So there they are. So I posted a bunch of Excels yesterday. One was up there before. I posted 3 more. I don't know if anybody saw them. If you don't have a computer to use these, and if you are going to use these, you still got to show work. So if you use these, whatever you're using, tell me what was in the cell location, what the formula of the one you're picking the number from. So this is this constant? Is this exponential, multi-channel, exponential, single channel, or arbitrary? That's correct. No one need talk. We're going to go with exponential single channel. It was one person taking it. We said the arrivals are 12. We said this per hour. And you switch that to whatever unit of time. 30. You ready? Now the question again is, what is the average time a unit spends waiting? A customer spends waiting. What's the average time a customer spends waiting?
0.02 hours.
0.02 hours. Key word he said was hours. Because if these are per hour, these times are being given to you per hour. But you got to expect a twist. And the twist is, how much time on average the customer have to wait in minutes? You got to realize you're being told the amount of time in hours because the arrival's in hours and the service is in hours. If 0.0222 hours would be 0.0222 times 60 minutes, because there's 60 minutes in an hour, will give you, what is it, 12 minutes? 12, or 2 minutes. No, 12 minutes? 2 minutes? 1.2 minutes? 1.332? 1.332, what's the next digit? Some confirmation? 60 divided by, or 60 times 0.0222. Confirmation, 1.332.
Yeah.
What's the next digit though? I want to make sure rounding.
3332.
Okay. On average, a customer waits, in this scenario, 1.332 minutes. I converted the hours to minutes. Real quick, same problem. Same problem. Every 5 minutes a customer arrives, we convert it to 12. We're taking their order, it takes about 2 minutes, we convert it to 30. Then the question says, what's the probability that the cashier is going to have time to work on his or her homework and not have to wait on anybody? What's the probability of that taking place?
0.6.
That's right. Wait, point what? 0.6. There's 2 that are probability. This one is the probability that there's no customers there in the system. This one's the probability a customer is going to arrive and have to wait. 60% chance, because of how fast the service takes place compared to the arrivals, there's a 60% chance, or really 60% of the time approximately, the cashier, him or her, will have time to do some homework or whatever, or help clean or whatever is going to take place. Everybody get this so far? The conversion. All right. So now, let's go here. We'll go to slide 20. I guess. All right. Burger Dome's management concluded that improvements in the design to reduce waiting times were desired. To make these improvements, the waiting line operation analysis often focuses on the way in the improvement service rate. Generally, the service rate improvements are obtained by either of these 2. Now, this is true. If you're managing a business and you're saying things are taking too long, customers are having to wait. I just had 2 customers leave from waiting so long in the past 2 hours. That's a bad thing. That brings your waiting costs so far up. So there's 2 ways of doing it. Either you increase the service rate through training or changing the design of how the service is being conducted in order to make the service take place faster. Or you add another channel, which is the most common way most managers will handle the situation. Those are basically the two choices. So now, Burger Dome has decided that they've decided we're going to go ahead and have a customer fill out their order on paper first, and then when they get and then hand it in, and when they get to the cashier, they're only paying while their order's already started cooking. So they're saying this is called an improvement on the system. They're not adding another cashier. Instead, they change the way it's being done to increase the time in which a customer will be able to get their food. So now with this new design, here we go. With the new design, the management estimates that the service rate will be increased from 60 to 75. So we're going, is that rate or time? 75, from 60 to 75 it says per hour.
Right.
It could say each hour or per hour, that's a rate. Thus, the service rate can be revised because we were using per minute, you divide by 60. If we're handling 75 per hour, that would be 1.25 customers per minute. These are both rates, and they're both service. The arrival hasn't changed, but I don't know it off the top of my head, but we'll see it here. The arrivals, what was the arrival here from the previous problem? The arrival is 0.75. So when we get to 0.75 per minute, okay, this is where we're at. Arrivals are 0.75 per minute. This is a rate. This is how many per minute. This is a rate, 1.25 per minute. They're both in minutes. And I want you to think for a minute, if you want to use hours, you're going to get the same answers, but they both have to be in hours. So if you're going to use 75 per hour, what will this be per hour, and how do you calculate it? 0.75 every minute is coming in the door. Say it again.
Times 60.
Multiply times 60, what do you get?
45.
45. So you can use per hour, per minute, you'll get the same answer. You enter those in, we're going to is this single channel still? So we're going to single channel right here. We're going to enter in, let's go with per minute. We want, and this was 0.75. And let's go per minute on service, per minute. And this is 1.25. Uh-oh. I can see I made a mistake. Hang on. Yeah. There we go. What's the average number of customers in the system? What variable should you look at?
W.
No.
Oh.
Average number of customers. I heard it up here though. L. Average number of customers in the system is how many? 1.5 customers in the system. In the system, you should always see that L is larger than L sub Q, because this is taking into consideration kind of like the weighting and the order taking, the whole system, where this is just the average number weighting. Same with this. This W should always be larger than the WQ, because this is the average amount of time waiting. This is the average amount of time in the system, which is partly the waiting also. In the whole big picture, if we just looked at the whole thing. So my question is, hang on a minute. I want to make sure you use the same units of time. You'll correct units of time based on what we entered. What's the average amount of time a customer spends in the system? Average amount of time a customer spends in the system. 2 minutes? That's right. Now, look at these numbers and watch what happens when I switch this to per hour. I'm not going to switch the words because I don't have time, but let's go with, what is it, 75 arrival? No, 45. Now I'm going to switch this to 75, right? Is that it? Notice, only 2 of the results changed. The answer is the same when I was using per minute. Do you see that? The only 2 numbers that changed are these 2. Because now they're not giving you the amount of time per minute, they're giving you the amount of time per hour. And if you converted, what was this one, 2 minutes? If you took 0.0333 times 60 minutes, it would say 2 minutes. But these always represent whatever these represent, which are now per hour. So, let's go back here. Here are those same things. The numbers were entered, it looks like per minute. Same thing, 0.4, 0.9. I just want to go back and forth real quick. Come on, right here. 0.4, 0.9. Look at the bottom, this one. 1.5, 0.6. These 2 numbers will be the same also. 1.5, 0.6. Forget the 7th one. We're not doing this in this class. You'll probably have an operations though. And then now, because they were entered in minutes, you have 1.2 and 2.0. But on ours, we switched it to per hour. So you have 0.02 and 0.0333. 2 minutes and whatever that is, 1 point something minutes. 1.2 minutes. The average time a customer spends waiting line has been reduced. Before, it was 3 minutes, now it's 1.2 because they're now filling out the order form, handing it over before they get to the cashier, so their order can start cooking while they're paying for their order. The average time a customer spends in the system went from 4 minutes down to 2 minutes, which is a better system. Let's go to 32. Now, suppose the management wants to evaluate the desirability of opening a second ordering process. We want a second cashier. Assume a single waiting line with the first customer in line moving to the first available server. Let's evaluate the operation characteristics of 2 servers. We're going to use all the previous information. Arrivals are 0.75 per minute, and service is 1 now. We're going back to the original. Let me switch this now. This is now 60 per hour and 1 per minute. If this stays at 7.75 per minute, 45 per hour. Right? All it's going to change is now we're going to have 2 service centers instead of 1. So let's go to multi-channel. I posted this, not that, here's the other one. That. I posted this. This is from the, in Chapter 11 for multi-channel, there's that page with that table. And I said, don't calculate that first probability, probabilities of no units in the system. You get it off that table, because it's much too large of a calculation. So in this case, it's whatever the arrival rate is divided by the service rate, and you go to that first column and match it. And then you go over here and figure out how many channels are we going to use to get the P sub O. P sub O is the probability of no units in the system. So our arrival, 0.75, divided by our service, 1.0. It's 0.75 per minute, 1 per minute. You can get the same answer if you took arrivals per hour, 45 per hour, service 60 per hour. Same ratio. It should be, what is that? 0.75 divided by 1 is 0.75. So our P sub O, if we add a second cashier, is what? 0.4545. So we got our first one. P sub O, 0.4545. Put it in words what this means. 45.5% chance of what?
There being nobody waiting.
No, nobody.
In the system?
Nobody even there. Yeah, in the system.
Okay.
No units at all. And that the both cashiers could go ahead and take up vape break. Whatever. You know. Well, whatever. I would say smoke break. I don't know. Anybody smoking? I don't know. Smoke if you got them? I don't know. So what am I looking at? 0.75. I'll just put it right there so you go straight across. So this spreadsheet, this is the first year I posted this, multi-channel spreadsheet. You have to enter the P sub O off that table, and it will calculate everything else for you. Okay? Let's start with, how many cashiers are there going to be? 2. Arrivals per whatever unit of time. You want to use hours or minutes? Just give me a number. 60 per hour. No, that's not arrivals. What, say I heard 45. You want to use per hour then? 45. Service per hour would be now 60. And the P sub O for 2 channels at a 4560 or a 0.751, same thing, is 0.4545. Now, all of these other numbers are correct. They're right off the right off the formulas. And let's say, I want to make sure you get this for a quiz. If you're somebody who's not going to be using this spreadsheet, you're going to find that little formula for whichever one of these I'm asking for, and you're going to hand calculate it. That's fine. It's not that hard. This one, you never hand calculate it. It will just take the whole quiz time to do it. So just use the table. The rest are pretty easy. But if this were a quiz and you're using this, you've got to tell me where you got the number. For example, what's the average amount of customers that are going to be waiting with this multi-channel system? The average number of customers waiting. Give me the number. That's right. Anybody hear what he said? Anybody got back there? L sub Q is the average number of customers waiting, 0.12272. If you're taking a quiz, you're going to say equals H4 divided by H5 to the power H3, da 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 da, and then see the different cell locations, H3, H4, H5, and H6. Just put in there, H4 equals, you can't see the numbers. I don't know which one's H4. H4 equals 45. H5 equals 60. Where's the other one? H3 equals 2.
Oh, I see.
And H6 equals 0.4545. That's all the work you got to give, and then give me the answer, 0.12272, or however you want to round it. And if you hand calculated this, you just entered all your numbers in and did the math on that. Let me try another one. Same thing here. You ready? What's the average number of customers in the system now that we have 2 cashiers? Average number of customers in the system.
0.87.
0.87, the L. So all you have to write is equals H8 plus H4 divided by H5. H4 equals 45. H5 equals 60. H8 equals 0.12272. That's all the work you have to show me on that question. Okay. Now, are you ready? For us to add that second channel, to have another cashier, it's costing us, I'm making this up, I don't think it's in your PowerPoint, it's costing us $11 per hour. Are the arrivals in service per hour up there? Because if not, I got to switch this to the unit of time that we're entering.
Per hour.
They are per hour, so I'm going to leave this per hour then. But if I had to switch it to per minute, because maybe we use 0.75 and 1, we would just divide this by 60 to figure out that cost per minute. This is the cost for all the expenses related with having another cashier being able to, take people's money. Management just informed us that because we went ahead and estimated what it would cost us if a customer walked out, if they did come back, didn't come back, and they said our waiting cost is about $7 per hour. So it's not a bad system, but there is a cost involved because there's still people waiting. It could be goodwill. In real life, this is a hard thing to come up with, but you'll be given that. Is that Matt? Let's check. All right? Matt, what day is it? I forgot. Monday? Today Monday? All right, just check. See, I have this on tape now, and I know he was late, and that way I can go ahead and mark it. How Tom is, and late? I'm sorry, late. I forgot. There we go.
Hey, Tom.
You ready? Economic analysis. My question for you is, how much is this going to cost per, this is hour, those are hours, how much is the overall system going to cost per hour if we have 2 cashiers?
11 times 2.
Here's the math. Cost per channel. I guess I got to start erasing. Cost per channel is $11 times number of channels. We're doing 2. Plus cost of waiting per unit of time, which is $7. This is 7, that's 11, times L, the average number of customers in the system. You answered that question, we have it highlighted, 0.87. I'm just going to round it. You calculate that out, you just calculated the cost per hour on average for this particular system based on that arrival, that service, the cost per channel, and the waiting cost. No matter if we're doing arbitrary, constant, exponential, multi-channel, exponential, single channel, nothing changes. You'll be given the cost per channel, you'll be given the cost of waiting, you'll be told how many channels. If you're not told how many channels and you know it's a single channel, what would K be?
1.
1. And all you've got to find is L. And so you don't have to, if you're doing this by hand, to get to there, we look this up on a table, we calculate that, and then we calculate that, you can stop. There's no reason to do the rest of these. That's all you need if the question says, conduct an economic analysis, what will be the total cost for this multi-channel system? And that's how you can get that cost. Somebody calculated this, we got 22 plus about 6, so we're around 28, 27 something, what is it?
28.09.
$28.09 is the cost per hour. If we have this in minutes, that minutes, the arrivals in minutes, service in minutes, this number would be a different number, which would be right there. We have to have the $11 per minute and the $7 per minute, because they all got to be the same unit of time. If that's in minutes, this has to be in minutes. If that's in hours, this is in hours, okay? It's going kind of fast, but man, it's all pretty much the same thing, you guys. They're all the same 6 characteristics. The economic analysis is the same no matter which one of these you're using. It's getting familiar with, is that a rate or a time? Is this a exponential service or is that constant service? What am I reading here? Do I have to convert any of these times? And then the rest is pretty simple.
Is the only time you need to use the table for piece of O?
The only time you gotta use the table for piece of O is if it's a multi-channel. Let's do this again. This is an overkill, but we decide that we wanted 3 cashiers today. 3 cashiers. And I want to know what if the overall cost will be more or less than what we're paying for 2 cashiers. And right away you say, oh, it's got to be more because you're paying a 3rd person. But L will be reduced significantly because there'll be such good service being done, which means that the cost for waiting will be down. Will the increase of adding another channel outweigh the decrease we're going to have in the waiting cost? What do I have to do? Let's see. This doesn't change. Still $11 per channel, but this changes. Now it's 11 times 3 plus. This doesn't change. It's still $7 waiting per unit of time, but this will change. This will be less than 0.87. I got to start by changing this to a 3. Arrivals are 45. Service is 60, but piece of O is now what? First of all, it was, what was the arrivals? 45 divided by 60, or 0.75 divided by 1 if you want to use minutes. You're going to get the same ratio, which happens to be what? What is it? 0.75. But 3 channels. What's our piece of O? Right there. 0.4706. So now I'm going to put 0.4706. Multi-channel. Whoops. Change this to 0.0746.
4706.
0.07 what?
0.4706.
0.4706. Thank you. Our L went down from 0.87 to 0.76. That's not enough. This is definitely going to be more expensive. 33 plus about 5, maybe 33.
38 plus 0.32.
So this equals 38.32. Okay. Yes, our probability of a customer waiting is so low. I mean, we couldn't be providing. We're the best customer service at a burger dome in the world. Our probability having 3 cashiers of them not being able to do anything and wasting time is like almost 50% chance of that because we're going to have too many cashiers, and it's such an overkill that our overall cost, taking the waiting cost into consideration, even though that went down a little, it's going to cost us $10 more on average per hour. So we would not want to have 3 cashiers. We're better off with 2 cashiers.
So did we convert to minutes?
You want to do the whole thing in minutes again?
So we convert, well, why do we divide by 60 then if it's not 5 minutes?
What did we divide by 60?
45 divided by 60.
45 divided by 60 is taking arrival per hour divided by service per hour. But we could use minutes, it'd be 0.75 divided by 1, which is the same exact ratio, still 0.75 no matter which one you use. That doesn't change, so the piece of O wouldn't change either. All right, so now I want to show you another example, but this time we're going to slide 43. Tell me what kind of problem you have here. This university student union has a self-serving copy machine. On average, 12 customers per hour arrive to make copies. Time or rate? Rate, because it says per hour. It's how many per or each unit of time. So that's a rate. The arrival process follows Poisson. The time to copy follows approximately a normal distribution with a mean time of 2.5 minutes and a standard deviation of 30 seconds. So let's just talk about the service. Forget about standard deviation for a minute. First of all, what kind of model is this going to be? Arbitrary. Very good. The service, time or rate? Let me hear you. Time. It says 2.5 minutes. It doesn't say 2.5 customers per minute or anything like that. It says 2.5 minutes. So we have to convert 2.5 minutes to the same interval of time that arrivals. Is arrivals per minute, arrivals per hour, per second? What's arrivals unit of time? Hour. So we have to convert 2.5 minutes to how many per hour? Per hour. I want you to imagine this. That's an easy one. I want you to imagine this. 2.5 minutes, the customer just used it. We're going to count them up. Another 2.5 minutes, we're at 5 minutes now, that's 2 customers. Another 2.5 minutes, we're at 7.5 minutes, that's 3. Another 5 minutes, we're at 10 minutes now, 4 customers. 10 goes into 60 minutes 6 times. So 6 times 4, oh, you said 12. 15. What is it? Did I do something wrong there?
Wait, you said it 25?
I did 20.
What's 60 divided by 2.5? Should be 24.
24.
Is it? Thank you. Should be 24. Stop. You had me going 15. 60 minutes, and you get the service happens every 2.5. There'll be 24 students have used that copy machine, got service copies in an hour. Our arrival rate is 12. So we got a 12 and a 24. This is 12 per hour. That's hard to keep track of the board. Now here's the deal. This has to stay in time. It's always given to you in time, and it needs to stay in time. But whatever you're using for the arrival per time and the service per time, the standard deviation has to be in that time interval. Everybody understand what I meant? For example, if we said the arrival was 12 per hour, but we said blankety blank per minute, the standard deviation has to be in minutes. The service, we said, is 24 per hour, so the standard deviation has to be in hours, and the arrival has to be in hours. They have to match. But the standard deviation is never changed to a rate. It's always time. So, what do we do with this standard deviation? 12 per hour arriving, 24 per hour being serviced. Standard deviation has to be in time. What is the time interval standard deviation has to be? Seconds? Can't hear you. Minutes?
No, it's got to be an hour.
Thank you. Thank you. He's covering for you guys. Hours. So 30 seconds got to be converted to hours. 30 seconds is how many minutes? Half a minute. A half a minute is how many hours? 1/16? Half a minute. Half a minute. If it were 1 minute, it would be 1/60th. But it's a half a minute, right? I hear a lot of answers here. What is the answer? How many hours? Somebody.
0.00833.
That's it.
Hours.
0.008?
Yeah.
0.0083. I'm just going like that. Hours.
Yeah.
And you start to say, okay, really, is that what I got to use for standard deviation? If this is in hours, if that's in hours, yes. Real quick, let's convert 12 per hour to how many per minute? How many minutes in an hour? 60 minutes in an hour. 12 per hour would be how many per 1 minute? So what do you got to do? Divide by 60, what do you get? 0.2 per minute. And then now take your service. 24 per hour is how many per minute? Go ahead, 24 divided by 60. What do you get? Point what? 0.4. 0.2 arrival per minute, 0.4 per minute service. Now we got to switch standard deviation to minutes. 0.5 minutes. A half a minute. If we took this now to per second, and that to per second, we got to take the standard deviation to seconds, which is given to us. 30. my point is, whatever you're gonna use for the arrival units of time and the service, that standard deviation has to be the same units of time. So, let's see where this goes. I don't remember. So we went ahead and switched it to per minute. 12 per hour, 12 divided by 60 is 0.2 per minute. Service, where's service? Takes 2.5 minutes, which would be 0.4 per minute. The math is a little different than how we did it. We got the same answer, 0.4 per minute. We first converted to hours, then divided by 60. And since this is per minute and that's per minute, 30 seconds gets converted to 0.5 minutes, a half a minute. So now everything's in minutes. We go to our arbitrary spreadsheet that I posted, which is right here. Arrivals we're using per minute this time is 0.2, is that correct? Service is 0.4 per minute, is that right? Standard deviation is 0.5, a half a minute. And the question says, what's the probability a customer arriving will have to wait? No.
0.5.
No.
0.5.
There it is. Probability questions are either the P sub O or the P sub W. And they happen to be the exact same number. You couldn't get this one wrong. If you realize that the question was asking at least 6 characteristics, 2 are probability, which are P's. 2 are the average number, which is L's. 2 are the average time, which are W's. The question was, what's the probability of of a customer having to wait, I think, if they show up. Is that what I asked?
Mm-hmm.
Which is 50% chance, 0.5. And then I could have said, what's the probability that there's no customers there at all, and the copy machine just sits and does nothing? 50% chance, the P sub O. And you got to show some work how to answer that question. When you're given a problem, if you're preparing for this quiz, it's all about, 1, recognizing which one of the 4 models this question is asking about, or designed about. Number 2 is the arrivals, and is the service in rate. And if it's not in rate, you need to convert it to rate. That's number 2. Then number 3 is figure out which variable is being asked. Only 1 or 2 of these are going to be asked per problem. It may be the average number of the system and the probability a unit would have to wait, for example. And you got to show some work. And look though, if you're showing the work, what did I say? Average number of the system. You're just going to say C5 plus C1 over C2. C5 is, we don't know what it is. And then you're going to tell me what C5 equals. C5 equals, wait a minute, is that right? 0.26. C1 equals 0.2. C2 equals 0.4. I know exactly how you calculate it. I know what numbers you use, and that's your work. Or you're just going to show me the math. You're going to take 0.26 plus 0.2 divided by 0.4. And you'll write that out. That's where the points are, right there. How did you get the number that I'm asking about? Then let's go to the other one I said. Probability no units in the system. You're going to say, either you're going to show me the work that you took 0.2 divided by 0.4, or you're going to say I'm using Excel, C1 divided by C2, and then tell me what C1 is. C1 is 0.2. C2 equals 0.4. And that's your work. Either way you want to do it, by hand or using Excel, but you still got to show the work. And if you're using Excel, you're going to say, oh, this is a lot faster, but you still got to give me the same things that someone's doing it by hand has to give you. So you're still showing the same work as far as the amount of work. So everybody's on a level playing field on how it's graded, whether you're using Excel or doing it by hand. Let's convert this to an economic analysis. We decide that per channel, it's costing us, we're going to switch this up a little bit instead of 11. $12 an hour is our cost per channel. Our cost per channel is $12 per hour, and our waiting cost is going to be $6 per hour. So, are you ready? Cost per channel. What number am I going to use? Number of channels. What am I going to use for number of channels? Let's start right there. Say it again. I heard it. 1. Because this is only one channel. This is arbitrary. in arbitrary, we're not studying multi-channel. So you know if you see a standard deviation, it's gotta be one channel. So this is gonna be a 1. What about the average number of units in the system? Average number of customers in the system, what number are you using? No, almost no. Say it again? 0.76, L. But that L is 0.76 average number of customers in the system per minute, because the arrivals are per minute, the service is per minute. So that L has to do with minutes. But this is an hour, this is an hour. Either you gotta convert those to hours or convert this to minutes. So take 12 and divide by 60 so I can figure out how much this cost for this channel is gonna be per minute. 12 divided by 60, is that this over here? Is that 0.2? 0.20 cents per minute is our cost per channel now. Number of channels, 1. Plus our cost of waiting, $6 per hour divided by 60 will be 10 cents, is that right?
Yeah.
10 cents per minute times L, which is already in minutes because our arrivals and service is in minutes, so 0.76. There it is. $2, that's 20 cents, I guess. 20 cents per minute times 1, 20 cents. Plus 76% of 10 cents is going to be 0.076, 7.6 cents. We add these together, we get 27.6 cents. I'm using the cent symbol per minute is our economic analysis overall cost. If you multiply that times 60, you'll have our overall cost per hour. But to make sure, let's use per hour. 0.2, if we take that 0.2 arrival per minute, what would that be per hour? 12. So now, we're going to switch that to a 12 to get our L. Service, 0.4. Switch that to per hour, 24. Our standard deviation has to be in hours. We had 0.008333, correct? Am I on it? 0.08333. If this is wrong, it's gonna screw us up. Here we go. Oh, hang on. Where's those 3? Long pause. I don't know how that works. Long pause. I don't know what that was. Here we go. $12 now, because we're using per hour. Number of channels, still a 1. Plus, now the waiting cost is back to an hour, $6 times our L when we use hours, 1.75. Someone's got to get into the math on this. So we got, this equals $12 plus 6, 4, maybe 4 more, that's about 10, 9 something, 10 something, what is this? 10 something, 9 something? Oh, stop, 6 times 1.75. No, it's just,
4.25.
no, forget the 12, 6 times 10 and a half, thank you. 10.5 plus 12 makes $22.50. It should be darn close to whatever this is times 60. What's 20? Take 0.276 times 60. And tell me if you get close to $22.50. 0.276 times 60.
1656.
Not even close. So forget that. Just the part where you forget that last little part. Again, because we put the arrivals and service an hour, we had to use the hourly per channel rate, and we had to use the hourly per waiting cost instead of per minute.
So you can't convert L directly from minutes?
Yeah, I can't convert L directly. That's what you just remember. Well, is the standard deviation wrong? That's why I left a 0 out. 0.008333. Rebecca, help me. Is that the correction you meant? Now, 0.76. Forget this. 0.76. Watch this turn into 16. Now, I just want the $6 times the 0.76 only. So that's got to be like 3 what? 4.56. Ready? $12 plus 4.56 is 16.56. Now, was this, take 0.276 times 60, is it anywhere close to 16?
Exact same number.
Exact. Okay, so now the theory is back in play. Woo! All right? So obviously we were able to catch a mistake that I made by leaving out one of the zeros. Everybody getting this so far? Economic analysis, I want to take it a step farther. There's a problem in the book that kind of looks like it's a multi-channel, but it's really a single channel, and this is a great example of how to do this. And how it's used in real life. This is exactly how I used to use it in this example. Well, there's a problem where two people are applying for the same job. I gotta find it. There it is, number 10. Anybody on page 489, if you happen to have the basic district. There's problems in the old edition. Oh, burn. Darn. Wasn't on. All right, I'm gonna erase the board because here's the deal. I'm gonna go ahead and put it right up here while that thing, I can't even tell if it's turning on. You ready? Here we go. Two employees are applying for a job at this tire repair place to do the old tire changes and stuff. All right? One employee, I'm up here on, is it, what did I say, what number?
You said 10.
Yeah, bring us down. You see it? Right there. Says to hire a new mechanic to handle all the tire changes for the customers. Two mechanics apply for this position. One can be hired at $14 per hour. And it says, and the service on average is 3 customers per hour. Is that rate or time?
Great.
3 per hour is the service. And then it says, another employee has applied for it, and it says this other mechanic can service 4 customers per hour. So we're going right here for the other one, 4 per hour, because this person's more experienced. They've already have done this somewhere else, and they know what they're doing, so they're faster at it. But for us to hire this person, it's going to cost $20 per hour. You're the manager. Which one should you hire? Huh? Let's run the numbers. You got it. You want to pay $20 an hour or $14 an hour? You probably want to pay 14. That would be my first reaction, right? But you got to take everything else into consideration. For example, what's our cost? There's our cost per channel for each of these people. But what's the waiting cost? And the waiting cost is the same no matter which one we hire. And if you look up there, it says, blah, 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 blah. Where's the waiting cost?
$30 an hour.
Yeah, the company's estimated that for all that's waiting, it's going to cost us, I'm putting waiting cost right here, $30 per hour. So this first person right here, this rookie, never done it before. We have to train him ourselves. Pay him him or her $14 an hour, and can handle 3. So I'm going to take 14 times 1, because we're only hiring 1. Even though there's 2 applicants involved, they're not doing the job at the same time. We're just hiring 1. And then we got to add to it this cost of waiting, which is $30. This is $30. That's 14. This is per hour. That's per hour. What goes there? Tell me what goes there. Not number. What is it we have to find? L. Let's do the other one real quick before we do this. This person is $20 per hour times 1, because it's just that person doing the job, no one else. We're only hiring 1. Plus $30 is the same waiting cost, L. But because they have different service rates, it's going to be 2 different L's. And we got to figure out one L and then the other, and then we can make a clear decision which one we should hire. Which one would be economically best for us because of that waiting cost. So, I'm going to go to single channel. Right here. The arrivals on that first person, what did the problem say the arrivals? We have, how many arrived? The garage has a arrival rate of 2 customers per hour. That's it? Arrival is 2 per hour. This person can handle 3 an hour, this person can handle 4 an hour, but the arrival's the same no matter who we hire. Who we hire does not change the arrival. So, I'm going single channel, putting a 2 on arrival, is that right? Did I just put 2 per hour up there? Okay. The first one can service, what is it, 3? 3 per hour. What's out? If you can see it. 2 per hour arrival, 3 per hour service. What is out? 2. Give me the total cost. 14 times 1, 30 times 2. That's $74 per hour. Am I correct? Help me out.
Yeah.
Now we're looking at the guy with a little more experience, or male or female more experience. They're going to get $20 an hour, but they can handle. All I got to do is change that to a 4. Oh, I got per minute up there, but we know it's per hour. 4. All right, what should be this person's L right here? 1. 20 times 1, 30 times 1, add them together, $50 per hour. Which one should we hire? It's the more expensive one. And I'm going to tell you, if we had not done this, every rookie manager's instincts say, well, I want to save the company money. I'm on a budget. I'm going to hire the $14 an hour. Not taking the fact that if this person's too slow, we could have some people leave or whatever the case may be. Things could back up, and there's a cost. And we've been told the waiting cost is whatever, I forgot what it is. $20, $30 per hour. Thank you, $30 per hour. Because that waiting cost is so high that really we're better off hiring the more experienced one, even though it's going to cost us a significant more money, $6 more an hour. Really, what percent's that? But in the big picture, we're saving money. Now, I want to give you a hint. This, what I just did, this economic analysis, 5 to 10 years from now, you're going to be in a lot of hiring situations. You're going to be managers, and you're going to be very happy you've been promoted because you're making more money you made your whole life until you're managing the people, and then you're going, how about my old job, man? All right? But anyway, you're managing people, and you want to hire the more expensive person. You calculate this, and if the overall cost, taking weighting in consideration, you can get approval to hire the more expensive person because you're showing the amount of money that would be saved in the big picture because of that weighting cost. This is the proof you need to get the authorization to hire the one that's more expensive because of how much faster that person can do the job. We're saving money in the big picture. Everybody get it? That's how that's used. That is exactly how it's used in a situation for a manager. How are we doing on time? 5 more minutes, and then we got to do it. It's just a small in-class assignment. Let me look at my notes here. We talked about how would a manager improve the characteristics of a waiting line. And I said there's 2 ways it can be improved, right? Changing the system to make it faster, or hire another channel, open up another service center. We talked about multi-channel exponential service, and we went into economic analysis so we could relate the 2. And how to use Excel, or if you're doing it by hand, to show your work on the quiz. Then we did arbitrary service. We did not do constant service. That's the only one I forgot. Let's go to, right here. On the screen. Here we go. Here's constant. There's a mechanical horse at the front of this store. And kids go up there to ride it. They pay 50 cents. They get to ride for 2 minutes. Everybody hear this? Hang on now. They pay 50 cents. They get to ride for 2 minutes. This is the service. It says time or rate. I heard it. Say it again. Time. Change it to a rate. They get to ride the horse for 2 minutes. That's the service. How many could ride that horse in an hour? 60 divided by 2. 30. Then it says kids are arriving at 15 per hour. Is that time or rate? This horse provides exactly a 2-minute ride for every child that puts the 50 cents in. The same 2 minutes. And that's what should jump out at you as constant. It's not a human providing the ride. It's a mechanical horse that provides the exact amount of time of service for every child. You get it? That's how you recognize constant. Everything else now is the same. you're gonna find L, you're gonna use the cost per channel, blah, 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 economic analysis. Wait, let's go to constant. I forgot what the arrivals are again. 30, is that what you said? Service is 15, arrivals are 15, service is 30. Here we go, right here. They're arriving at 15 per hour, right? Is that right? And then the service, they get a ride for every 2 minutes, so 30 children could be serviced in an hour. And then the question will say, what's the average number of children having to wait to ride that pony? What's the average number of children having to wait? Half of what? No. What's the average number of children having to wait? Katie, I see that you have it. Give it to me. No, McKenna. No.
0.75?
What is it?
0.75?
No. The average number a child has to wait.
0.05.
No, not 0.05. No, you gave me every answer but the one. 0.25. Brittany, did you have it? That way you left.
No, I was looking at the average number of systems.
Yes, that's right. I'm not asking for up. I said the average number waiting. You guys got to have this in front of you for this quiz. You got to have everybody's 6 characteristics names and their variables. So you do not give me the wrong answer. The average number of kids having to wait is a quarter of a kid. Meaning there's not a lot of waiting going on. Matter of fact, what's the probability a child walks up to this pony and has to wait? What's the probability this time? Say it again. 50% chance a child walking up to ride the pony might have to wait. 50% chance. All right? Hang on, man. Almost there. What's the average time a child spends in the system? The whole thing, waiting and getting on the horse. Average time. 0.75, nothing. 0.05 what? 0.05 what? Hours. 15 per hour, 30 per hour, 0.05 hours. If I need to change that to minutes, how will I calculate it? 0.05 times 60. And that will tell you how many minutes. You guys, I'm getting scared.